My name is Brian Kettleson, and I'm here today to talk to you about best practices for deploying Linux on Azure. In our discussion today, we're going to talk about some of the options that you have to run Linux on Azure. We're going to go over the roadmap of these talks because this is just one of a four-part series. We'll talk about some best practices that you can put into place now, and then we'll demonstrate those in action. So first, let's start with your options for running Linux on Azure. Of course, the number one option is running Linux on a virtual machine. We can run Linux and Windows virtual machines, and we have a wide variety of sizes to fit your workload needs. You can run anywhere from 1 up to 416 virtual CPUs and up to 12 terabytes of RAM. I would love to have a machine with 12 terabytes of RAM. You can use these for application servers, database servers, web servers, anything that you would want to run a service on. These virtual machines can be sized perfectly just for those needs. Another option is app service. This is our platform as a service. This allows you to rapidly scale web and cloud applications. It's a managed platform, so you have access to all of the different services that Azure provides, and you can deploy anywhere from 1 to multiple instances instantly, and it will scale to meet your needs. App service is perfect when you need to do rapid deployment that meets critical performance, security, or compliance requirements, and high demand applications. App service is the perfect Black Friday application scaler. Azure Kubernetes service is Microsoft's managed Kubernetes instance. It's highly available, and it's a fully managed Kubernetes, which means that Azure takes care of the control plane for you, and you just bring your compute. It has end-to-end integration with DevOps and CI/CD, and it gives you rapid development cycles that Kubernetes is known for, along with the ability to maintain the enterprise governance you already have. It allows you to simplify and standardize your application deployments. We also have a few other specialized options for running Linux, including Azure Batch, Azure Container Instances, Azure VMware Solution, and Azure Cycle Cloud. Azure Cycle Cloud is kind of interesting because it allows you to create a HPC cluster on Azure's instance. Who doesn't want their own Beowulf cluster? I'm ready. Sign me up. So let's talk about the roadmap of this four-part series. In session 1 today, we're going to talk about how to take virtual machines and run them on Azure with Linux. We're going to do some setup automation, and we're going to do some partially automated provisioning. So we'll get the machines almost ready for production. And we're going to position ourselves for growth. This is the most important part. When we start off this project, we don't want to put ourselves in a place where we have to throw away the work that we've already done. In stage 2, we'll be able to scale up what we've already built with load balancers, virtual machine scale sets, and we'll be able to protect our investment with backups and disaster recovery. Stage 3 will bring us into containers, and we'll containerize our applications and orchestrate their deployments on Azure Kubernetes service. And then finally, in stage 4, we'll add security, monitoring, and CI/CD. So in this four-part series, we'll grow from tiny startup all the way up to a fully grown-up enterprise application that's ready for anything you throw at it. So let's talk about the best practices for this stage 1. I selected a small set of best practices that we can apply quickly and easily that will position us for good growth in the future. The first is using the ephemeral disk for swap storage. Azure virtual machines come with an operating system disk and an ephemeral disk. The ephemeral disk is a temporary disk that has a small amount of storage on it, and it's not guaranteed to persist between reboots. So using that ephemeral disk for your swap space on Linux allows you to have better performance because swap is enabled, and you don't have to use a disk that you've bought somewhere else. Ephemeral disk comes automatically, and we just need to set it up to use as our swap partition. Another best practice is to add a second data disk for application storage. The boot disk for operating systems on Azure VMs is optimized for fast boot times, but slower storage retrieval. If we want fast performing storage, we need to add a data disk that has better I/O throughput, and we'll use that for our application services. We also want to add application security groups and network security groups to partition our traffic and protect our network from possible intrusions and keep us secure. The combination of application security groups with network security groups allows us to take like VMs and put them in groups and then apply security policies to those groups. So we can say that the database application security group is not allowed to talk to the internet directly, and it's only allowed to receive traffic from the application server. We also want to be able to restrict remote access to a limited subset of internet addresses. We don't want the whole world to be able to SSH into our servers. We might want to restrict that to just your office subnet or even your home IP address. We're going to use tags so that we tag everything, and all of our resources will have tags that we can search and find them easily. And then finally, we're going to use a declarative tool like Azure Resource Manager or Terraform to manage our infrastructure. This will position us for rapid development and easily changing the scale of our systems in the future. So let's take a look at a demonstration of these in action. I've created a Terraform setup here that shows off some of the recommendations that you saw in the presentation a moment ago. I chose Terraform because I hadn't used it previously, and I'm a big fan of declarative infrastructure development, and I wanted to see how Terraform worked with Azure. I was quite pleased with the results. We created a Terraform file and a group of additional files that manifest our infrastructure using this declarative format. So we require the Azure RM Terraform provider, and then start simply like we would in the portal by creating a resource group for everything to live in. I've put all of the common infrastructure bits in this main.tf file. We create a virtual network, and then a subnet on that virtual network, and a common network security group for all of the machines. Finally, I create a data source that pulls my own IP address from ipifi.org, and I use that in the security group so that I restrict SSH access to these machines to only have my source IP address from home into these machines, so no other network address can SSH into these machines. You could, of course, change this into a subnet or do something different, but this allows me to have relatively good restrictions on SSH access into this system. Moving on, we've got 3 Terraform files, one for each of the systems that we plan to start. We've got an app server, a database server, and a web server. And then we've got a file called variables.tf, and this stores variables that we're going to use for this run. So let's look at these individual files. The app server declares a virtual machine called app.vm in the location that's stored in our variables inside our resource group. It then creates a network interface card for it. We declare the size of standard DS1 v2, apply the tags that are in the variables file, and we apply this custom data section, which is in a file called appdata.txt. We'll get back to that in a moment. For the operating system disk, we call it app.os disk. We give it read-write caching, and we set the storage account type to premium LRS. That gives us much faster read-write access on SSDs. The source image will be canonical Ubuntu server at the latest version. We'll call it prefix app.vm, and we'll get the admin username and password from our settings file. We'll disable password authentication in our SSH server so that you have to use an SSH key. Therefore, we have to define our SSH key in our configuration, so it's going to pull the SSH key from our configuration file. We add managed disks for storage. In this case, we're using a 100 gigabyte disk at premium LRS storage. And this is because the disk that's attached to the OS is not optimized for data retrieval and storage. It's optimized for fast boots. So we want storage on a separate disk from the OS disk. This also allows us to detach this disk and attach it to another VM in case there's a problem with this particular virtual machine. We attach the disk to the virtual machine using this Azure VM disk attachment stanza. And then we create the network interface that is attached to the virtual machine. Finally, we create the security group association from that network to our security group, give it a public IP address, and then attach it to an application security group. If you remember, I mentioned application security groups as a way to bring machines together as a common resource type and apply network controls to those resources. If we have an application security group for app servers, we can apply rules to that application service without having any problems when we upgrade, create more machines, create fewer machines. That application security group will allow us to apply that policy to the set. So here in this next line, we use that application security group and apply it to the network interface. And finally, declare our public IP address. The database server is roughly the same with just some different variables. So if you scan through that, it's almost exactly the same. We just have different names for the devices. And then the web server, also similar. Now, I mentioned that we were using this custom data. This is a way that you can send either a bash script to be executed or a cloud init file to be executed when the machine is created. So inside this custom data, we're base64 encoding the contents of the file webdata.txt. Let's take a look at this because this is a cloud init file. And this cloud config has a few stanzas that tell us that we're going to update the packages. So it's going to run apt update and then apt upgrade. And this is on first boot. And it's going to install nginx full, the package nginx full. And then here's the interesting part. This took me a bit to figure out, but it's really exciting that we can declare how to set up the disks from this cloud config. So I've told it to use the temporary disk, the ephemeral disk that's attached to the virtual machine, and give it a master boot record partition table and set 100% of it as a Linux swap file. So this 82 is the code for a Linux swap file format. And we're going to set that up as a swap file system. And then when the machine boots, we'll take that partition and mount it as swap. And that's really exciting because we don't have to do manual partitioning after the machine is booted. The other cloud configs are similar, except they don't install nginx. So we've installed nginx on the web server, but not on the app server or the database server. So let's take a look at what this looks like when we run it. First thing we need to do is type terraform init. This initializes Terraform. It creates a .terraform directory, downloads the plugins that we've declared in our Terraform app. And if everything's good, you see a lot of green. So we'll try Terraform plan. Now it's asking for our admin password. If you look at the variables file again, we have defaults for nearly everything except for the password. So we'll create a password that nobody can break. And it's going to refresh the state. So it's going out and asking Azure, do you have a resource group with the name that I've specified here? Do you have a virtual machine with the name that I've specified here? Since Terraform is declarative, it's asking Azure RM if we've got these devices already configured. Since we don't, the output here shows lots of green plus signs because it's going to add these things to our Azure account. So if we type Terraform apply, we'll enter our password again. And we'll watch as it goes off to Azure and again refreshes the state to make sure that these resources that we've requested don't already exist. And it gives us the final prompt. Are you sure you want to do this thing? So we say yes. And we watch it take off as it goes off and starts to create the bits that we need. Terraform is smart enough that it knows the relationships between the stanzas that we declare. So it will create the resource group before it tries to create a virtual machine. It will create the disks and the network interfaces first, and then attach them to the virtual machines. While all of that runs, let's go back and look at the variables file. and see what other variables we've declared in here. We declared a location of EastUS2. I used my initials for the admin username. And then I created a prefix, and almost all of the resources in this Terraform system are going to have a prefix of stage 0. And then I created a list of tags. Our tags for this stage are called iteration 1. So everything in our dashboard will have a tag of iteration equals 1. That way we can search for them if we want to delete these later. And then an SKU variable for the Ubuntu instances that we might want to run. And then the path to my SSH key. So we're going to take that SSH key and it automatically gets uploaded to the servers and allows me to do passwordless login to those servers. So we can see our virtual machines are still being created. In previous iterations, it's created the network, it's created our app security group, our network security group. All of those pieces are in place. So the last thing it's got to do is create these virtual machines and then attach the disks to them. Overall, I really enjoyed the Terraform process. I'm using Terraform version 0.13.0, and the documentation was really clear on both the Azure documentation website and the Terraform website. And I found lots of good examples on how to operate with Azure and Terraform. It seems like a really well-matched group, Azure and Terraform. I haven't used Terraform on any other platform, but I was really pleased with how well it worked for this demo. Now our virtual machines are created. So it's taking the last part and attaching our data disks to the virtual machines. And as they get attached, those cloud init files will be running in the background. And we're all set. So we can see that all of our disks have been created, all of the virtual machines have been created, and the machines have been provisioned with the information that we've requested in our cloud configs. So we've got quite a bit of automation taken care of already with very little bit of work. And this sets us up for really simple modifications in the future where we can evolve this into a much more complex platform with more services and more machines without having to throw away the investment we've made in creating this layer. Now that you've had a chance to see these in action, my challenge to you is to take these best practices and apply them to your infrastructure. If you have more questions, you can go to microsoft.com/learn and see the thousands of tutorials, documents, and other guides that we have available for you. You can also see the sampled GitHub repository at https://cda.ms1z big B. My name is Brian Kettleson, and I hope that you'll continue this journey with me as we evolve our architecture into full automated deployment. Thanks for joining.